that we use an algorithm to answer that question, and if we can always answer it, if we can always accept or reject the string and the given language, then that language is decidable. And by deciding the language, we indirectly solve the problem. Now, I know I'm still being vague, but we're getting there. Right. So by first examining problems that when translated into this language style of presenting the problem, if those are decidable, then we have a solution to our problem, and that too I'll explain next board. So it's useful to start with examples of languages that are decidable, and we'll go through those example after example progressively until we come to examples that are undecidable. Okay? So having a knowledge of examples that are decidable will help us appreciate those examples that are not decidable, that are undecidable. Okay? So we'll go through examples that are decidable first, and then later, in fact that'll be section 2 of this chapter, they'll be examples of undecidable languages, and hence through indirect reasoning, therefore the problem is not solvable. But we'll get explaining why that is for next session. All right, so that's what's saying here. All right, so now we're going to start with examples of decidable languages. In other words, there is an algorithm, there is a Turing machine that can decide that language. In other words, every string in that language will be accepted by the Turing machine, by the algorithm, and any other string will be rejected. Okay? Then that's what decidable means. So we'll start now talking about decidable languages, and to be a bit more specific, we're going to start with regular languages. Now they're a rather narrow category of languages. Next board we'll do subsets within subsets within subsets and so on, of various categories of languages. If we start with a very small subset, would be regular languages, and regular languages are a subset of another category of languages, and that category in turn is a subset of an even broader category of languages, and so on. Go up about half a dozen levels or so. So we're starting at a very low level, the so-called regular languages. That was chapter 1, if you remember the text, and then followed by, in chapter 2, context-free languages. And regular languages are a subset of context-free languages. Okay? So we already have 2 levels now. So we'll start with these, and a bit of revision. What is a regular language? It's a language that is recognized by a finite automaton. So finite in the sense it doesn't have infinite memory, right? It has a finite number of states, that kind of thing. So the memory that it does have is implicit in the states of the automaton. Okay? And you cannot, now it's a finite automaton, it has a finite number of states, so you cannot have an infinite memory. So finite automata cannot solve problems that involve an infinite amount of memory. Okay? Whereas a Turing machine does have an infinite amount of memory that's also entirely accessible, whereas the stack-based automata, the PDAs, push-down automata, they do have infinite memory, but that memory is not infinitely accessible. You can only access what's on the top of the stack. So the PDAs can do more than the finite automata, but they can do less than the Turing machines. Right, so we start with regular languages, and we will give you three categories, three problem types, and then use those one by one and show you how you can translate a particular problem, computational type problem, into membership of a language type format. You're translating the problem from a fairly direct computational type problem into membership of a language type problem, and the two are equivalent. If you can answer one, you've answered the other. It's just a different way, a different perspective. And when we give a few concrete examples, you'll see. So, what are these three categories of problems? Three types of problems. Well, here's one. You're given a finite automaton, right? And you're given a string. And the question is, here's the problem: will this particular automaton, finite automaton, whatever it is, will it accept this particular string, whatever it is? Okay. And can you find an algorithm that will answer yes or no to that question? Answering yes or no, in other words, accepting or rejecting, is that's deciding. Okay, so that's the problem, a computational type problem. Find an algorithm, or put it this way: is there an algorithm that will answer yes or no to this question? Will this particular finite automaton accept this particular string? Right? In all its generality, it could be any finite automaton, it could be any string. That's a very broad general question. And is there an algorithm that would answer yes or no to that question? Right? So you may then ask, well, how do you translate a problem like that into language, into a question about language? Well, that's what we're coming on to. Now, but before we do, here are a few other type of computational type questions. It's a bit, well, sort of whether a language of a finite automaton is just empty. If the language consists simply of the empty string, so wiggly brackets epsilon, or just wiggly brackets nothing. I have a bit of a question mark about that. Right. Okay, and the third category of problem is you're given any two finite automata, say A and B, and you're asked, are they equivalent? Now, two machines. If they're equivalent, there's a bit of revision. What does that mean? It means that the two of them recognize the same language. In other words, they do the same job. They're equivalent in that sense. They perform the same task, and their task is recognizing a language. So if they both recognize the same language, those two machines are equivalent. But it's any two finite automata, A and B, any two. Is there an algorithm that can answer yes or no whether any two of these finite automata are equivalent? Right? Very general question. Again, can you find a Turing machine, an algorithm, that will answer that question, yes or no? That's the problem. And in all three cases, how do you translate these problems into the format of a language problem, asking whether a particular string belongs to the language, because that's what it boils down to. I keep alluding to that, but we're getting there. All right. Now,